Okay, so we're back to renormalization in 5-4 theory in 4 dimensions. And now we're going to look at how renormalization affects the coupling constant. So last week we did the mass, or last time we talked, we did the mass. And to figure out how the mass is renormalized, we looked at the propagator. We looked at the following one-loop diagram involving the propagator. For the interaction vertex, we'll use this diagram. So before we continue, slide exercise. So this is the full diagram where I haven't amputed the external legs. 3 such diagrams will contribute, right? You have 1, 2, 3, 4, 1, 3, 2, 4, and 2, 4, 1, well, yeah, 2, 4, 1, 3. So this is ST and U channels. Bear that in mind. But now if I cut off the external lines, what will the amputed diagram be a function of? An odd way to phrase a question. You see here, I had a P, I had a K, right? And then I was integrating over K, it's a function of P, right? So here I have many momenta flowing around. So let's start by asking, I'll start by asking what constrains these momenta first.
Nothing really.
Is it, well, there's only one momentum that's unconstrained, that's K, which is flowing over the loop.
Yeah.
Otherwise, it's just the conservation momentum that K1 and K2
Very
should
good.
be equal to K3 and K4.
Yep.
Very good. So in fact, let's break this apart, right, for a second and see that it has to hold vertex by vertex. Right. So first of all, I borrowed this figure from Z's textbook, and he's already done something here, which has used the conservation of momentum, right? So the fact that you can write K1 plus K2 minus K and K here, right, is using the fact that you have momentum conservation here. Generally, let's say this is K3, this is K4, right? Sorry, K5 and K6, because K3 and K4 are flowing here. Then K1 plus K2 has to equal the sum of these two, right? And basically, you're eliminating one in favor of the other, right? If I call this K5, then I have, K1 plus K2 minus K5 is K6, right? And similarly, I would have a momentum conserving vertex here, but as Shire Neal said, K1 plus K2 has to equal K3 plus K4, and then if I include this intermediate step, I'll find that this still holds, right? So if I was going too fast, just remember, there's a delta function that conserves momentum at every vertex, right? And follow the arrows. So I K1 plus K2, and then I have minus K3 minus K4, right, in the delta function. So that's all great when I have external momenta. Now, if I'm to ampute all the external legs, what would I have left?
Just the bubble.
Well, but I mean, what is the unintegrated momentum?
The K. You haven't
No,
defined K anywhere.
K is the integrated momentum.
Okay.
It's K1 plus K2, which we can call P if we like. Or alternatively, K3 plus K4, which is like minus P. Right?
Well, if
So
you cut it out, then K1 and K2 would be 0.
not quite. So you see here, I've in some sense cut out the propagator itself, but I still have to account for the momentum that was flowing here. Right? Otherwise, I can't make sense. I mean, the delta function will not be. I mean, I have a delta function that I have to impose at the vertex, so that won't be satisfied. So similarly here, I have this kind of amputed diagram. So in the conventions of Marcus Ludi, whom I borrowed this diagram from, K is the same as this K, but then P is minus of K1 plus K2, right? Or K3 plus K4, alternatively, is P. So it's still a function of one unintegrated momentum, right? So now let's try and proceed with writing down what the Feynman rules are for this. So do we have any guesses? So what would we have?
Each one the matrix element.
Yeah, so what am I going to be handling here? Actually, just give me a second. I'll pull up something that has the conventions right. But so
are there three diagrams crossed?
Yeah, so there's definitely 3 cross diagrams, but let's just take one. Let's take this channel for the time being, right? And then we'll include the other 2 channels. They just all add up together. So yeah, just give me a second. But okay, so when we had the renormalization of just the propagator with the one loop diagram, then we integrated over one propagator, right? Going in the loop. So here we're going to have 2. Just give me a second. Yeah. So I'm going to have one propagator that looks like 1 over or minus I over k squared minus m squared plus I epsilon. And then I'm going to have another one which is k plus p squared minus m squared plus I epsilon. But the m I'm going to be using is going to be the bare mass, right? So let's evaluate this. Okay, so sorry. 0 squared. Because we have 2 vertices, right? I have 2 factors of I lambda. And then this is going to be divided by 2. And then I'll have my integral. The only integrated momentum is k. Okay. And then I have 2 pi to the 4th power. This is just the Fourier transform. And I'll write down the Lorentzian propagators first, and then we can look at the Euclidean ones, because we're going to be analytically continuing. So I have k squared minus m, oops, m naught squared plus I epsilon times much of the same, but instead of k, I'll have k plus p. And so first step, we're going to rotate back to Euclidean signature, right? So what will happen is that I just have lambda square over 2, and then I integrate over for k, let's see, sorry, d4, so ke. Did we use this notation with e in the last episode? Otherwise, we can just drop it and then just use k, and we just know that if we have minuses instead of i's, then we're talking about Euclidean and not.
I don't think we did. So
yeah, that's fine then. So we'll do it like this, and we'll have 1 instead of k squared plus m squared, m naught squared really. And then we'll have 1 over, let me just make sure that, no, it'll still be a minus, or plus, no. It's just gonna be a minus, k plus p squared minus m naught squared. Right, so let me just check if my conventions are the same from the past. Yeah, okay, no, it changes to plus. which makes sense. Because in some sense, m is the time component of the 4 vector. And so if you're taking the Euclidean norm, then I'll be taking the sum. So now, question is, how are we going to simplify this? Actually, okay, so we're going to use something called the technique of Schringer parameters or Feynman parameters. It's either called Schringer's trick and Feynman parameters or the other way around. I never quite get this right. But basically what we want to do is, instead of having this, we want to really just have something like 1 over propagator squared, right? Instead of having this k and k plus p. So there's a way to simplify our lives. So in this specific example, it'll be to introduce k, which equals k plus xp, right? And so this is a 4 vector. And x is really just a number between 0 and 1. And what we'll do is also introduce a parameter m squared, which equals m naught squared minus x, sorry, this is m naught squared minus x into 1 minus x times p squared. Okay, this is many manipulations. But say we did all of this, then what will happen, let's call this m naught squared, is that we'll have squared over 2 times the integral from 0 to 1. This might seem very arbitrary, but we'll go back to this this rule because there'll be something interesting if you were to be able to do all of the k integrals and then just look at it in terms of x integrals. Then it's almost like you're doing the integrals over only proper time. And this is something close to the heart of what's called the Whirl-line formalism, and generalizes when you do string perturbation theory and string theory. But it also relates to a lot of the modern amplitudes techniques, and there's some interesting geometry that goes behind doing the integrals only over these Schringer parameters. So let's separate out some constants. I have 1 over 16 pi squared, and I'm going to do the same thing as before, right? So I'm going to have, let me put the integral after this actually. So I'm going to do spherical polar coordinates, and then I'm only going to integrate over, I'm going to do the integral over the angles, and then only integrate over the norm, but I'm going to integrate over the norm only up to a cutoff, right? That was what we were doing last time. And then we'll have dk squared, right? Where k really is the norm, right? It's the norm of k. And we're going to have k squared over k squared plus m squared. Oh, sorry. I'm out of practice with live LaTeXing. This is what happens when we don't have an episode in a couple weeks. Okay, so then we have something that's easier to evaluate, at least near the upper edge of the integration bounds, right? Because there k squared is much larger than m squared, and we can sort of see what it's going to end up like, right? It's going to end up like integral dk squared over k squared, right? So it's a logarithmic divergence in lambda, right? In big lambda. So, or if you want, you could just do the integral, and let's see what Mathematica gives us if we did the integral, right? So I'm going to momentarily switch to my Mathematica screen. Titled, yep. Okay, so you're seeing this?
Yep.
Cool. So our integral is, so it's called k squared y, right? So I want to integrate y over y plus m squared whole squared as a function of y. Mathematica is better at doing the indefinite integral first. So you see we get this, and then what we're going to do is evaluate this at y equals lambda squared. And y equals 0. Sorry, it's not doing what I want it to do. I'll have to do it separately. 2 lines. Right, and then I just subtract the two things. And then I take a series in lambda. Right, so Mathematica doesn't like simplifying logs, but basically this is like log lambda squared over m. Well, let's see, something's up. I haven't subtracted them properly. To put some brackets here because I want lambda. Yeah, you see it's log lambda squared over m squared with the
Shouldn't
1.
there also be like some constant thing? Like, wasn't there supposed to be like the Euler Maccheroni constant or something somewhere?
Not here. I mean, in other integrals you would encounter it. Here it's fine. So we did we encounter it last time? No, we didn't encounter it last time either.
No, we didn't. Yeah.
We encountered it in the quantum mechanics examples. Because, okay, so how the Euler constant would appear is if you have something like the integral representation of the gamma function. And then you expand or something.
That would show up when we need to dimensionally regularize things.
Exactly,
Dimensionally
exactly, yeah.
renormalize things, sorry.
Yeah. So in dimreg, you would see it. And there, instead of having something like a log lambda squared divergence, you would have epsilon appearing. And yeah, getting Mathematica to do dimensionally regulated integrals is a little bit annoying.
I can't handle dimensional regularization. It just blows up big time.
Yeah, I mean, it just doesn't know what all that means exactly, right? So what you need to be able to, I mean, maybe I'm just not being clever about it. But basically it's better to look up a table of integrals when you're dealing with dimreg. And we'll get to that too. So for our purposes, what's going to happen here is that the result of this integral will be sorry, just the integral though, not the x integral, just this integral. So let me separate that. Equals 1 plus log that's right. Okay, so I have lambda squared over m squared. Squared. Right? Huh?
I forgot to switch from Mathematica
Yeah,
to
we're still on Mathematica.
Oh, right. We're in the wrong screen. Sorry. Yeah. Let's go back. Great. I see we have this, but remember that m squared here is a function of p. Okay. A function of p. Right? And remember that p was like k1 plus k2 square, and it's a function of p squared, which means it's like k1 plus k2 squared. And what is k1 plus k2 squared if we have 2 to 2 scattering? It's Mandelstam's S. And so as you can imagine, the other channels will contribute with T and U, right? So you have Okay, so let's put our result together, and then we're going to have our x integral sitting on the outside. X integral doesn't do much because, well, okay, it'll hit what's inside m squared, right? Because m squared is like x times 1 minus x or whatever. So we could, yeah, let's see if we can simplify all of that, if we even have to. Okay, so let's put the total result together. Up to the x integral. Okay, so it's going to look like I squared to pi squared, because there's a 2, and then multiply 16 pi squared, integral from 0 to 1. Okay, and then we have dx. The 1 plus the log of squared over m squared of s. Sorry, this came outside. S. And I just copy this 3 times. So this is, so this, where did, so now I'm adding the other channels. So if I add the other channels, this will become 3. And then I'm going to have E, and I'm going to have U, right? Plus terms of order 1 over lambda squared, which we're dropping. So what, okay, so let's just see what S, T, and U are so that we're not confused about it. So S is defined as K1 plus K2 squared, right? T is defined as K1 plus K3 squared, and U is defined as K1 plus K4 squared. So these are the 3 channels.
K1 minus K3 and K1 minus K4.
Minus K3 and
Because that
K1.
affects that you'll get a negative sign, right? Because these won't be conserved.
Right. No, but I mean they're squared, so if you swap them, you're not going to see a negative sign.
Because, like, okay, in the massless case, it's supposed to be negative 2 K1 dot K2. Or not, sorry, it's supposed to be negative 2 K1 dot K3 for the T channel.
T channel?
Yeah.
Let's see. Whoa. Wait. Okay, then maybe there's a typo somewhere.
Yeah, because like it's K1 plus K2 equals K3 plus K4. And
Right.
then you square each of them, right?
Right,
So
right.
K1 minus K3 squared equals K4 minus
Okay.
K2
Is it
squared.
the same for you?
Yeah, same for you. Yeah.
Okay.
So S is the only one that gets the plus sign.
That's plus. Okay, thanks. Cool. So I don't know why there's an equals and an equivalent sign. Okay, cool. So we have these 3. And basically, it's like saying I have K1, K2, K3, K4, K1, K3, K2, K4, K1, K4, K2, K3. Right? Those are the 3 diagrams that would contribute to this process. And the idea here is that when I ampute the legs, P is just one of those sums. Right? And the sum just carries over, right? Because K3 plus K4 equals K1 plus K2. So if I had this combination here, the same thing it's constrained over here. And so in 2 to 2 scattering, these are the 3 Mandelstam variables. And this is my contribution. So let's see if we can get Mathematica to do this integral. It might not be entirely necessary when we're just deriving RG flow equations, because we're just going to be looking at derivatives with respect to lambda of everything. But let's see if we can still get the full result. Okay, so if we're ready, then I will switch screen sharing to Mathematica. Great. So our function is something like log of lambda squared divided by m squared. And what was our definition of m squared? Well, it was little m squared minus x times 1 minus x times s, right? So s, t, or u, whatever. And I'm going to integrate this x 0 to 1.
I have a feeling it's going to like.
Well, maybe this is the wrong way to feed it to Mathematica. Maybe instead, what I do is I do this. So I know that it's log of lambda squared minus this. Okay, well, while we're rating, someone might actually be able to calculate this themselves. Actually, definite integrals are also not Mathematica's friend. So let's do indefinite. Okay, great. Now what I'll do is go x to 0 and x 1 and do a subtraction.
I think the second time you substituted x equals 1, you kind of deleted an x.
Did I?
Yeah. It's in the
Okay.
log.
Sorry about that. Aha. Okay, great. Thank you, Sharon. You're very sharp. Whoa, that's not good. Maybe I subtracted the same thing from the same thing. This is 0, right? And that should go in here.
Can you run
And
one
then-
again?
Yeah, let's just run one
Wait,
again.
didn't we evaluate the integral from 0 to 1 and then we're just subtracting the two results?
We evaluated the integral as an indefinite one, and then we're just taking the two bounds and subtracting. Yeah, so as you can see, it's some annoying function of s and m squared, but here's something we can do. We can do trig to x so that we can see it in terms of logarithms, and then we can full simplify it. Oh, full simplify takes it back to this form, so let's just keep it as a log. So yeah, this is basically what you're getting. It's the one loop contribution. Great. So now let me go back to my screen. I mean, we won't really be needing that for the rest of the exercise, because if you remember, the rest of the exercise involves taking derivatives with respect to big lambda, right? And trying to derive RG flow equation. So what we want to, okay, so what's the observable of interest here? It's the one PI diagram with 4 external legs in some sense, right? 4 amputated legs. And so in convenient notation, in other words, Lutti's notation, it looks like this. Oops. Let me just get it on Finder again. So if I could resum all of the 1PI diagrams, then I could evaluate this exactly. Here, I just go up to one loop. Right. So what you get when you run the derivatives through is something that looks like this. You get lambda, d little lambda naught over d lambda equals 3 lambda naught squared over 16 pi squared plus higher corrections, lambda squared, lambda cube, and so on. Right. So this is our RG flow equation for the coupling constant. So if you wanted to, you could have done this in terms of the renormalization scale. And what we get is something like d lambda renormalized over d log mu.
We'd have an H bar. No.
Oh, you would have h bar, but I'm setting it to 1. We're using these units right from the start, so we're not keeping track of that. But yeah, I mean, one loop is roughly equivalent to 1 h bar.
Right.
So I'd have 3 lambda naught squared over 16 pi squared. This would be lambda r, sorry, the renormalized coupling. And this is just because the form of the RG flow equation doesn't change where you evaluate it, right? If you're evaluating it at the cutoff scale, then in the bare coupling satisfies the same equation as the one that was satisfied with the renormalized coupling at an arbitrary renormalization scale, right? Going back to all our exercises from before. So this is how you, okay, so now we have a beta function. So we call this beta of lambda r. Okay, that's our RG flow equation. So great. The meaning of it is not all that different from what we've already understood about the running of couplings even in the quantum mechanics example. But there's a few things here that we should probably go into a little bit more, like, for instance, the Feynman parameters, and try and see if we can connect any of that to the Whirlline formalism, because that I think would be worth doing.
Before we go there, I have a question about what we just did.
Please.
So the equation that you just gave us, where you took the derivatives with m0 and m0 and m0 squared and lambda naught, so you just, like, it's just one equation, and we want to kind of like redefine lambda naught and m0 squared.
Mm-hmm.
So how do we do that, given that we have, it's just a simple linear algebra question of we have two variables and one equation. So how do we find exactly how to redefine the two of them?
No, but you know independently what dm naught squared over d lambda is, remember?
That's the one we did last time?
Yeah, it's this.
Okay.
So you plug that in. Okay, so you plug this relation in this middle line. Right, so that'll eliminate this part, and then you're just evaluating a derivative of a known function of m naught squared. Cool. Oh, thanks for the question, though. So
the question I had, sorry, before we go on, it's the same thing here, where you had when you're taking the derivative with respect to lambda naught, right? So this is fine for the S-channel diagram, because we even like once we validated, we saw we had root S in the denominator, which is perfectly fine.
Mm-hmm.
But in the T-channel and U-channel diagrams, there will be poles, because you can have K1 and K3 or K1 and K4 being collinear.
Well, okay, so good point. There are, okay, so what you do is figure out how to cross, right? So okay, let's see what happens with the T channel and U channel diagrams. You do want there to be collinear divergences. I mean, there's some physics behind them. You do want there to be even soft divergences. But you can still use the derivative. Okay, so let's see what happens if I just took the derivative even in the S channel. Let's try to work through that a bit more slowly because we have time. So let's take the derivative with respect to M. Actually, we need to check where the lambda dependence went in all of this. There's something that confuses me about our calculation earlier because the log lambda squares just cancel, right? Big lambda. So the first derivative term that's there in our RG flow equation, the overall RG flow equation won't hit anything. It's the second two that might, right? So we have to add, we're very concerned about the M derivative of our end result, right? The derivative with respect to M, because the lambda derivative is trivial, right? So we have to see how these two things combine with each other. So let's try to do this a bit more slowly. Okay. Okay. So let me share with you my Mathematica screen once again so that we can go to Sharon's question. Great, so you're seeing this? So let's start right here. Let's do this slowly. So we have three integrals really, right? Let's see if we can get Mathematica to evaluate them all at the same time. They all look kind of the same. It's just that you have to remember T and U have a minus sign implicit in them, which is an important thing as we're just learning. Great. So we get the same kind of arctan function, and we do have poles, right, in U and in T. So let's just see what happens near. Okay, so let's just see what happens near the collinear singularity, right? It looks fine. So tree level, I agree, probably have something to worry about, but I'm expanding this function and around t equals 0 and to whatever order, it only looks like it's growing. So really the leading order it'll show you it's just log of lambda squared over m squared. And x goes 0 to 1, so fine, it's fine. Now let's take the U channel. I mean, the U channel will do the same thing near collinearity, right? So this is a bizarre function. And when you Taylor expand it, you're hitting logs with the derivatives, so you're bringing down some complicated function, and the 1 over square root t's might cancel. So I guess I'm not too concerned about collinear singularities just for the one loop contribution.
So did we just get lucky, or is this
Is there some deeper reason?
Yeah.
That's a very good question. I wish I knew enough about amplitudes to answer this well. Okay, so undoubtedly, if I just looked at okay, so if I had no loop there, so if I was just looking at the tree level contribution, Okay, at tree level, what do I have to look at to start to worry is the first question. Just the vertex doesn't mean much. No, I mean 5-4 theory is weird. I don't see a simple 2-to-2 scattering process because I don't have a cubic vertex. Right, if I had a cubic vertex, it would kind of be like, you know how you do in QED, you just have a cubic vertex between the electron and the photon, so you can easily do that. 5-4 theory, the simplest thing to do is close a loop. So I don't know what to tell you, honestly, Sharnil. But let's see. Okay, so this is a log divergence of some function of S. Clearly, I mean, something worse might have been happening. Well, okay, so let's just look at the integrand.
No, wait. The root t divergence, there's 4m squared minus t in the numerator itself. So the root t should kind of cancel out in the series expansion. Right?
Yeah,
Like in the
that's what's
arctan term.
happening.
Yeah. Plus there's
Yeah.
also like, and there's also like in the series expansion of arctan itself, there's root t's in the thing too. So
both numerator and denominator, yeah. So that's why you're sort of safe. But okay, so this is kind of like the same structure as what's in the integrand, right? And that too doesn't seem to have any qualms with t going to 0, the log here.
yeah, because you're saved by mass squared term. Right?
Exactly.
Yeah.
Exactly. So definitely, okay, so I guess we're discovering the reason why massless theories are more prone to collinear divergences and massive theories. So 5-4 theory, clearly, if we took mass to 0, we're going to start to have problems, right? But yeah, I mean, massless theories, you will not only have collinear but soft singularities, right? So you have to worry about the norm of the form momentum itself going to 0, as in when you have a really, really low energy massless particle, or when you have collinear external leg and massless particle. There you tend to talk about different particles, though, or different fields, right? So you have an electron and you have a photon or something like that. Whereas here we're really talking about just one species of particle, so it's hard to extrapolate the lesson. But anyway, good question, Sharon. And this is something we should meditate about more in the future, I think. But let's proceed. Okay, are there any other questions people have before we do a deep dive on Schwinger parameters? Because honestly, this is something that I'd never fully appreciated until I had these amplitudes people that impressed it upon me, saying, oh, you do integral only over finite parameters. It's kind of like doing the integral only over proper time. And so I was like, oh, really? Okay, I didn't know that. And there's some deep intersection theory magic that's going on with this simple realization, apparently. But yeah, anyway, any more questions right now? No, then I'll proceed. So let's go back to Mathematica. Okay, so the idea is that I want to separate 1 over AB into an integral over something times a function involving a plus b. So because I can handle a function a plus b. AB is annoying. So let's just look at the claim. Sorry. Create 1 over x times a plus 1 minus x times b whole squared. So let me do this in a bit more slick way so that we don't have to look at intermediate expressions. Res x1. That's the basic idea, right? So in our example, we basically had A being a function of P, B being a function of P, right? So then we can ask, can we extend this to like, well, what would we like to extend it to, right? We would like to extend it to something like 1 over A, B, C, right? So how would we do that? Or you want to extend it to something like 1 over A power X, B power Y, stuff like that, right? Those are the most general kinds of integrals you're going to be seeing at any loop order, right? They'll all kind of look like that. But first, let's see if we can derive this result. And for the record, the Wikipedia derivation of it gets to the heart of the whirl line story. So let's see if we can appreciate this. So first of all, what is our trivial observation when we were doing quantum mechanics perturbation theory? We found these propagators coming from an integral of an exponential, right? What was our story there? Do you remember? It's something like e power h I h t, where we integrate t, gives us this, right? So then if I took this and I had e going to minus infinity, well, okay, I mean, this is 0. Okay, so let's do this in Euclidean signature so that Mathematica knows what I want it to do. Come on. So I want to take minus e going to, so this is going to decay to 0, and then I have t going to 0, which is minus 1 over h, right? So if I take infinity to, so 0 to infinity, the integral of e power minus ht, which is a continuation of e power iht, gives you 1 over h. And remember that we were doing this with the non-interacting Hamiltonian, right, with h0, and that was giving us a propagator, right? So really the propagator is like 1 over the momentum space representation of your free Hamiltonian, right? And that's always true, right? In quantum mechanics, that was true. In field theory, that's true, and so on, right? So now let's rediscover where that's coming from in the whirl line formalism. So do we agree that we can write 1 over AB as 1 over A minus B times 1 over B minus 1 over A? It works. So then let me take this bizarre combination and then do a substitution. So what I want to do is take U equals Z minus B B. Well, okay, this isn't quite working because I have to introduce an integral. So the claim is that I can recover this by doing an integral uh, 1 over z squared z okay, so take this function at z goes to a, subtract the result, z goes to b. right? So this is 1 over b minus 1 over a, which means that if I took this, okay, let's see if I can, let me try to be a little bit wizard-like. Never mind. So I'm just going to do this instead. Cool. So what will we do first? We did some algebraic manipulation. We took 1 over ab, wrote it as 1 over a minus b times 1 over b minus 1 over a. Number one. Number two, we introduced an integral that recovers 1 over b minus 1 over a, which is just the integral of 1 over z squared, which is 1 over z. 1 over z. We evaluated a and b. So that's step one. Now, what's step two? Well, let's take this function, right, which is the indefinite integral, and then introduce our friend u, which is z minus b. Let's do this. Not solve, but yeah, no. Let's do solve. Z minus b over a minus b, right? And then let's do, right? So what is the thing we see here? Let's take that polynomial out. Minus ua plus 1 minus b whole squared. Oh, this should work. Okay, let's see if I made some mistake. No, because there's an integration measure that I have to include, right? So okay. Let's do this. Let's just see if it works. No, it's not gonna work. So what's the Jacobian of the change of integration, right? So I have function, which is this. Okay, so it's dz, right? I need to change dz to du, and that comes at a cost, right? So du is dz over a minus b, right? So let's see what happens if I multiply function by a minus b. Great. So do we recognize this? This is nothing but our, okay, so let's do u goes to 1. U goes to 0. Right, so if I had 1 over a minus b, then I'd had these contributions. So in other words, if we were doing the u integral, then what I would do is I would take this quantity, I would square the denominator, and then integrate with respect to u. And then I would take the integration bounds. I would get the result I wanted. U goes to 1 and u goes to 0. Right, and this gives us the function here when we subtract the two results. So this is a very annoying derivation. I don't know if you think like this, but I certainly don't. I wouldn't be able to reproduce this for you tomorrow. So what's a better way? Better ways to use our intuition from the world line, right? So where did our intuition from the world line come? It came from doing integrals like this. Integrate the exponential of, let's just stick to Euclidean signature for the time being, right? So I get something like this, and then I evaluate this at s equals infinity minus s equals 0. The numerator goes to 1, I get 1 over a, minus 1 over a, right? So now if I had product, okay, never mind. Mathematica doesn't like taking that to 0. But let's take s to 0. Just remember that when you evaluate it at the upper integration bound, it goes to 0. And the lower integration bound, the numerator goes to 1. And then you see how you recover essentially the kind of products you would want. Okay, so sorry. Let me see if this is really working. No, I shouldn't do just one integral. I should do two integrals. So I do s, and then I do minus s1 b. Right. So now you see I have to take both s1 and s2 to infinity and 0. So basically, I could do any product in the denominator by just doing multiple integrals of this form, right? And then I just keep putting whatever my result is into the numerator, right? So this is a very simple integral, so we can even do it back in type 4. We don't actually have to do this in Mathematica. So what we have is that one times an, right? This is much more ambitious than anything that we tried before, right? Is basically the integral from 0 to infinity times dsi, right? So I goes from 1 to n. So let me do it differently. Let's just do ds1 all the way to dsn of the exponential minus s1 a1 right? So it's not quite as nice as what we were doing before, because there we had only one integral. Here we have a lot of integrals. The integration bounds are a little bit different also, right? So how can we improve our situation a little bit? Well, first we do some substitutions, right? Let's define an alpha, which is the sum over the s's, right? All the way to n. I starts at 0, right? And then let's define some index quantity, which is s sub I. So we'll normalize each of the s's by their sum over all of them, right? So you see, we want to go from integrals from 0 to infinity to integrals from 0 to 1. So you have to be doing some kind of normalization for you to be even to conceive that you can get there, right? So now our integral goes from 0 to 1 for all these alphas, right? Let's do it this way. This the product I 0 to n, right? But then I still have this integral. 0 to infinity. So you see, I'd have to pull alpha out and then multiply each of the individual terms by their respective alpha I, right? So then I have the sum I equals 0 to n times alpha I. Actually, let's do n minus 1 because, okay, let's do it this way. I. And then we're going to have the last term, which is constrained by the fact that the sum over all the alphas equals 1. So we might as well use that, right? Plus 1 minus the sum over I equals 1. Are we doing 0? I don't remember if the indices started at 0, but I don't know if that matters. Do you agree?
Yep.
Multiplies a n. So, which is the easy integration here? We have two options. We have to do a series of a product of alpha I integrals, or big alpha integral, right? Sorry, I haven't put the integration constant here. So, right, so we just do the integral over this sum. That's an integral we know the form of in principle, right? As in we've encountered this kind of thing before. So let me clarify a little bit what's going on up here. I don't think I've denoted it correctly because there has to be an alpha even here. So what is the basic integral that this is if I take away all the craziness? It's the integral d alpha power n minus 1, right? Times the exponential of minus alpha x. Where x is my fantastic sum over all these kinds of things, right?
Yeah.
So how would I calculate that? We're field theorists now, or budding field theorists at least. So we like introducing series of derivatives with respect to the argument, like we would with sources, right? Of a basic integral we know how to do. Do we agree?
Yep.
This is homework to show that it's going to be, it's not hard homework by any means, but you're going to get this. Because the integral of this exponential is just going to be 1 over alpha, you know. So you're just going to keep taking derivatives with respect to x, and then you're going to develop a series in 1 over x, and you get this. Great. So now, what is x? X is this awesome sum. So Let's do this. Product. Sorry about the 0, but this is what I really meant. Minus 1 factorial times the integral. So the relief that you can take is in the fact that we're not going to evaluate the alpha I integrals. The point was to get it to the form of the alpha I integrals, right? So that's like the Schwinger parameters. If you could evaluate the alpha I integrals, you can do arbitrarily high loop calculations. But the point is that arbitrary high loop calculations are only evaluations of this class of integrals. At least you can take peace in knowing that now.
Right.
N equals 0, not okay, let's do 1. I to n d alpha I. Sorry, let's do n minus 1 again because we have a constraint.
Yeah.
Okay, this is going to be awesome. Sum. This is one of those latex symbols that when you want it, you don't ever remember. Right? You put the squiggle, it never show up. But then when you don't want it, it's always there. Am I doing 1? Yeah, I'm doing 1 to n minus 1 of alpha I, a I, right? Plus one minus the sum, right? I equals 1 n of alpha I. Let me do a different index just so that we're not getting confused. These are different sums. I'm doing the entire sum here. Then I have a sub n, but everything to the power n. Don't forget.
Yeah.
Okay, we can make this a little bit better, right? So whenever you see some kind of conservation, what are you tempted to do? Introduce a delta function.
Right.
Right? Because this thing, it's annoying. So let's at least make it look better. So finally, we have n minus 1. So this equals n minus 1 factorial times the product of integrals from 0 to 1, but the product is over I. This will not be a very popular episode for a while, I think. Okay, so really it's up to n now. Here it's n minus 1. It's just really up to n here.
Right.
But what's the cost of doing that? I introduce a delta function. Well, we had better notation for that too. J equals 1 to n j divided by finally something that looks half decent if you write it in nice notation. K equals 1 to n of alpha k a k, everything raised to the power n, finally. See, this is the overall complete generalization of everything you wanted, right? Arbitrary product. Now, question. If I had an arbitrary product, but with powers, like 1 over alpha to the power x 1 over, so 1 over a to the power x, 1 over a 2 to the power y, what would I do? Well, let's just take the clue from this very nice Wikipedia article, and I'll just paste it in here. See, all you do is do some differentiation with respect to a1.
Similar to what we did.
Exactly, at an earlier stage.
Mm-hmm.
So this is great, but at least it makes sense. Like what we were doing with this 1 over a minus b stuff, I don't know. Here it's direct. I know this one integral. What's my one integral? Integral 0 to infinity. Yeah, here's my champion integral, right? Integral 0 to infinity of e power minus s a is 1 over a. Right, I have a product of these integrals. Step 1. Step 2, I introduce the sum of these s's and then the ratio of any one with the sum of the whole, right? And then I just do the change of integration variables, right? Right, this looks ugly. Something's gone wrong. Okay. Right, so I do a change of integration variables. That's all that's going on here. Then I remember my okay, but I have to remember that there's an alpha n minus to the power n minus 1 here, right? Because every ds is like alpha d, like, you know, everyone is contributing an alpha.
Right.
And then there's an alpha integral. Then I do my alpha integral. And I get the result that follows from that. And then I rewrite it in terms of a delta function, right? So you see all these Schringer parameters or Feynman parameters are secretly what? They're secretly proper times, sort of normalized proper times. So these are like, as I said, these are higher loop diagram evaluations, right? Like why higher loop? Imagine that I took, so say I had a theory with a quartic vertex, but also a cubic vertex. Then I could draw a line here. I'd have a two loop diagram, right? So then this two loop diagram is going to involve integration over one more propagator.
Right.
So
Also have, won't there be two integrals you have to do because there'd be two undetermined momenta? For one for each loop?
Yeah. So you're going to have to also deal with the fact that it's going to be overlapping divergences and so on. But the idea is you play this game, do the momentum integrals, and then get it to just this form where you have these Schringer parameters sitting outside. Right. So that then you're good to go. And Amplitude's people tell me there's something deeper to all of this, or at least that this realizes something about intersection theory and stuff like that. That's above my pay grade, but one day we might examine those claims. So yeah, guys, I thought that this is a good stopping point. Is there any questions?
I'm still trying to go through the
steps.
I don't have a question as much as this is kind of relevant to what I was doing, what my research project now is on. And there's actually something interesting here. It's like, so the thing is, what really, if you go up to the, could you just scroll up to the Feynman diagram, right? So what saves us here is that we're dealing in a scalar theory. We're working purely in a scalar theory. So when we have the momentum integral, there are no k slashes in the numerator that we have to care about, right? And that really saves us. Because what happens when you get to k slash, right, even naively, it's going to be divergent because you have k cubed in the numerator. Then in order to deal with that, you need to go into dimensional regularization, right? But then there's a problem. You have k slash, you have uncontracted gamma matrices, right? And then you have to deal with how to represent gamma matrices in your t minus 2 epsilon dimensions, and that gets really nuts.
Yeah, there's these evanescent operators and stuff like that. I had a friend who did a project where he did an infinite resummation of evanescent operators in 2 plus epsilon dimensions. In order to, he was working on some non-Fermi liquid states, and yeah, that was crazy. Well, it would be very fun if you could walk us through that, Charniel, because
Oh no, I
this
have
is
I have no idea about that. There's actually
Okay.
on a slightly different tangent. Like, so the thing is, when you have like there's actually another interesting way to solve it, and this was found in, I think, the 60s by Pasadena and Weltman, and then Toft used this idea to solve to do his complete one loop renormalization of QED and stuff. But the idea is that when you have like one power of L in the numerator, so you basically have L mu, right? So then you look at all the possible single index Lorentz invariants you can have. So that's in the case of this thing, there are only 3, right? But there's K1, K2, and K3, because K4 is completely determined once you know the other 3, right? So then you basically express that integral over K mu times whatever the denominator is as some coefficient times K1 mu plus some coefficient times K2 mu plus some coefficient times K3 mu. Then it just becomes a linear algebra problem of finding what the coefficients are by contracting the numerators and stuff. And then you can get like a nice recursion relation and you can solve them. So, but then the cool thing is, like, it always reduces to scalar integrals, which are integrals with no nothing in the numerator. And then like the classical algorithm is just to use like Feynman-Schwinger parameters and you'll be done.
Right.
When you have like, I don't know, something like a box diagram, you'll have something to the 8 in the denominator, which is absolutely horrible to deal with. But
yeah, well, no, that's a really powerful tool. Thanks for bringing that up. We should actually go through calculation doing that, because it's super useful, right? When you use
you don't want to.
No,
the thing
very
is, like, you just
generally.
stick it into Mathematica at this point. There's this thing.
Yeah.
There's the Mathematica package that you can just stick it into, and it, in principle, does it for you.
Yeah, but you want to do at least one, right? You want to be able to
just
do at least one of these things. And the nice thing about knowing how to break things up into kinematic invariants and form factors is that it's really useful, and it's something that generalizes beyond perturbation theory. So beyond perturbation theory, these are the kinds of things that you can hope to use, right? Like because you don't know in general, which has some form factor, you have some idea, right? So CFTs, you can use this in momentum space. Actually, you can use award identities to constrain the forms of integrals that you get. There's something called the triple K integrals, not to be confused with another organization that has 3 Ks, but I don't know why they wanted to name it that. But anyway, there are these Bessel K functions with momenta as the arguments, and there'll be a product of 3 of them. And you have to do it's horrible integral. I mean, I don't know how to actually do it, but if you meditate hard on the analytic properties of this integral, you can learn a lot about CFTs.
If you do want to just go through one of these calculations for next time, I have a series of lecture notes which I learned from, which I could send your way, and then we could do that next
Sure,
time.
yeah, it would be nice. It would be nice to go through one of them, so that we have some satisfaction of going beyond the scalar case. Of course, there's other things we should cover in principle before getting there, but we're not actually doing a lecture series. So, we'll get there when we do. Sweet. So
stop it now.
Yeah.